Hi, in this video I'm going to reverse this handlebar clamp. It's made from aluminum, so I will try to reproduce this part with the 3D print nylon and probably a polycarbonate to see if I can reduce the weight and still get the functional part by using a 3D printer. So the part is held to the steering stem by using this pin and also one of the M6 bolt here. Because the handlebar is held to the stem by using the friction from the compressing of the clamp, so I will do a stress simulation to find the weakest point of the original part to see how much this part can handle in terms of loading, and then I will redesign the part for 3D print, adding some stiffener so that the nylon or polycarbonate can substitute this part. I'm going to use Creality scan Raptor Pro for making this 3D scan. So I make two scans. First one, I will scan the top face here, and then I flip over and then make a second scan to scan bottom side, and then I will merge it together using the Creality Scan 4, the new version. The surface of the object is kind of reflective. Because the object is quite small, I will put some of the external marker like this, and I will place magnetic markers 4 on the table so that I can use it for reference removing this turntable. Anyway, you can just place the object directly onto the turntable like this. But I prefer to raise it up a bit so that I can scan more of the side here, because I'm going to merge to scan together. It's the best to get the side area scan as much as possible. So I will raise this up a bit using cube and some pyramid. Place it like so. This is Creality Scan 4, version 1.1.4. I'm going to make a new scan. This part is quite small, so I will use 0.2 for the resolution, and I will scan in a power line mode. Let's start the scan. Okay, so you can see that the turntable is a matte black color. It's picked up very quickly, but the object, which has a bit glossy surface, is picked up, but it's quite slow. It has a sandblast texture and it reflects light. So if you find this when you scan black color object and it's a bit of a glossy, I suggest that you spray it. You get a result faster. SKDS2. Okay, here's the spray part. Okay, let's try again with the spray. Okay, can you see difference? Let's pick up immediately at the same resolution, 0.2. So here it's all done for the top, but I need to scan the side. Using the spray, we make a 3D scan goes deeper, so we need to scan the sides as much as possible. The leaning angle of the Raptor is very high, so you can just lean it on the side like this and capture size area very easy. Some laser 3D scanner cannot do this with this angle, and when you merge it, it will be much easier to merge when you have all the side there scanned. Okay, so it's all done. Okay, next I'm going to pick up 3 points, hold the shift key and click on the 3 points of the flat marker that I placed on the turntable, and I click on create a plane. So the red color will be erased. Click on the check mark here. So now we save some time not to manually remove the turntable. Yeah, I have already sprayed the bottom part here. Okay, click on a new scan. Okay, it's quick, isn't it? It's 0.2 resolution. Okay, I'm going to try to scan all that area. Okay, it's done. Clipping plane function. I'm going to hold shift key, pick on the 3 flat markers, create plane, check mark, complete. diffusion using a 0.2 resolution. Okay, so we have 2 scans, and I'm going to merge it. Let's try automatic alignment. Okay, so automatic alignment works just fine. So I'm going to export this point cloud for reversing with the Autodesk Inventor. I have to export this one by one. Handlebar clamp 1, and then I'm going to export the second scan, handlebar clamp number 2. Okay, here's in the cloud compare. Drop in the point cloud. So I will merge these 2 scans together, merge multiple clouds. I'm going to change the color, change to light green color. Okay, next I'm going to align flat face to the XY plane. So I will click on 3 points, alignment to 1 and 2 and 3. So now it's aligned to the XY plane. And then I'm going to align it to the XY axis by rotating it along the Z axis. I use my monitor, corner of my monitor to align this. And next I'm going to move this center of the box to the origin point. Click on Tools, Registration, move bounding box center to origin. So now it's all done. Next I'm going to check the quality of the scans. Slice it to a very thin layer. See, you can see the precision of the scan. You have a very clean and thin lines. Autodesk recap. Just drag and drop LS files here. Okay, all done. Click on Save. Okay, attach, open. I choose insert at origin 0.001. Okay, so it should be at the origin point. Let's turn on the X. Okay, this looks like it's in the center. Let me check. Draw a box here. Yeah, it's close enough. Only 4 microns, so I will just leave it. Create a study and assign the materials as the aluminum 6061. Next I'm going to create a constraint, create a pin here, and frictionless on this both sides, and frictionless on this side, and pinned in here. Okay, so we have a close approximation of the physics of this object. Next I'm going to apply force on this face going up direction. At 1000 kilograms load, this part will break. So I think it should be somewhere around 500 kilograms. This part can carry 500 kilograms of load. And if you look at the displacement, it's only 21 microns. You're probably going to bend the handlebar before this part start to break. Okay, so if I want to change the materials to nylon 6, let's try 200 kilograms, 2000 Newton. A breaking load for this part when it's printed with the nylon is 200 kilograms. For the safety, this part, the limit load should be 100 kilograms. So I don't have to add any stiffener. I can just print this. Okay, here's in the Creality slicer. So I'm going to print the parts with the PETG, nylon and the polycarbonate. I will place it in this orientation, and for the wall loops I'm going to choose 3 wall loops, and infill I'm going to change it to 100% infill, and for the support I'm going to use 3 support with the default value. So it's going to take about 40 minutes, and it's right here 23 grams. So let's check again after printing. Okay, next I'm going to print with the nylon polymaker. And for the polycarbonate, I'll use the Kexel K8 filament. Okay, this is a nylon print. Okay, the printing has finished. I print with 3 filaments. The first one is PETG in white color. This one is easiest to print and also the fastest. See, the overhang is quite nice and clean. It's almost no strinking, and when I bend it, there's some flecks that I can see. And the second part, I print polycarbonate. Polycarbonate is also very easy to print, and the overhang almost the same quality as the PETG. There's no stringing, and the support is quite easy to remove, and you can sand it. I have tried to sand it. The print bed temperature has to be able to reach 110 degrees Celsius, so some printer maybe cannot print this, and also you are going to need a heater chamber. When comparing PETG to the polycarbonate, it's quite very close in the appearance, but the polycarbonate is much stronger. This one is 70 megapascal, while this one probably somewhere around 45 to 50 megapascal in the tensile strength. And the one that I have, the polycarbonate from Kexel, it's stiffer than the PETG. I can feel it when I bend it, this part. The nylon is the most difficult to print because it's, you see here, it's the ability to print overhang from the nylon is bad. I mean, this is 45 degrees overhang, and it doesn't do very well. I mean, when I print this, the printer used a fan cooling on the side fans, and part fans also apply to this print, but it cannot. See here, it cannot climb up even 45 degrees angle like this. So nylon is difficult for a part that requires overhang, and the support, I mean, it's most difficult to remove. I need to cut it with a side cutter to take them off, and you cannot sand it. I can tell you that you cannot sand nylon. It's not going to give you a smooth surface. Before I print this one, I dry it with a dryer for 8 hours, 80 degrees Celsius, but it still give me stringing. If you have an emergency part printing, like many of my customers, they work in a factory, their plastic part break down, and they need to do emergency print, so that while they're waiting for the part to arrive, they still can function their machines. If they use the nylon, they have to dry it for 8 hours before they can start printing. But with the polycarbonate, they can start printing immediately. Nylon has a higher melting temperature. This one is somewhere around 120 degrees Celsius. It starts to melt, but the nylon has a better heat resistance, and for the strength, it's comparable. This polycarbonate is even stronger than the nylon, 70 megapascal versus 60 megapascal for the nylon. Aluminum part replacement, I think polycarbonate wins for this comparison, because it's easy to print. I mean, if you have a modern printer. Same way I do with the aluminum. Okay, so it's tight, no movement. So the bike weight is 22 kilograms. Yeah. Can lift off the whole bike. Okay, this will be very tight. Okay, so there's no sign of cracking anywhere. So PTG is working if the part is small. And there's still some clearance here. Okay, let's try with the polycarbonate. So I'm going to pre-tension it a little tighter. Let's try it some more. Yeah, I can see it has a less deformation. The gap here is wider than the PETG. Obviously, it's wider. Yeah, this gap between the mounting face is wider than the PETG, so it's stiffer. This one is obviously stiffer than the PETG. So I can tighten it a little bit more. I tie it too much. Okay, so I over tightened and it breaks off. You can see here. So the polycarbonate is very stiff, and if you apply too much initial force when clamping, it doesn't flex much. So the stress around the bolting area is very high. So it's break off. So I'm going to give a polycarbonate a second try and reprint this part at the same one, but this time I will reduce the clamping force, the initial force that used to create a friction to the handlebar. Because the polycarbonate is very stiff comparing to PETG, it means that when you clamp this polycarbonate part with the same deformation, it's going to create more of the clamping force than the PETG. As when you apply too much force on the original aluminum parts, it's going to crack and break. I need to apply just enough force to create a friction between the part and the handlebar. Yeah, this should be tight enough. I can't twist it. And with the polycarbonates, the print quality is much better, and also the precision of the print is better than the nylon. But you see here, as the gap here is almost the same as the aluminum part, but with the PETG I will have a smaller gap to create the same friction on the handlebar. So it's quite stiff, the polycarbonate. I think you can just replace the aluminum with this. Let's see if the nylon will behave like a polycarbonate, because I can feel the flex. It's flex like a PETG. A little less, I think. Let's see how it holds up. The nylon requires more clearance than polycarbonate. I have already used a 6.5 drill bit to drill out. This is what happens when you print nylon with a 100% infill. It's going to give some error in the dimension of the holes. Okay, let's put this on. So I'm going to do same tensioning as the aluminum. I can hear a cracking sound. But nylon shouldn't break. I think I see a layer line separation here. Original parts, 46 grams PETG, 22 grams, so it's less than half of the aluminum. Nylon, 19. Nylon is lighter than PETG. Polycarbonate in 2 pieces, 19. So the polycarbonates and nylon weighs the same, so but they are all half the weight of the casting aluminum.